Hello everyone. Today we're going to be doing chain rule, multivariable chain rule, and implicit differentiation in multiple variables. Okay. So I guess typically, we look at what it looks like in single variable, and then we move on to multivariable, which for this one isn't really all that different. So we know that if you have y, which is a function of x, right? But x is also a function of t, so you could rewrite this as like y, which is a function of x, which is a function of t, and you wanted to find the derivative of y with respect to t, you would do dy dx times dx dt. And for me, what makes sense about this is the units. The units make sense. So say dy dx was like miles per hour, and then dx dt was like hours per gallon, then dy dt would be miles per gallon. And obviously multiplying these results would cancel out the hours and give you miles per gallon. You could kind of think of it the same way here. You could cancel out the dx's, even though by themselves I don't think they actually have quantities or like something you could really cancel, but it's a nice way to remember it. So yeah, that's single variable. Now multivariable. Oh, before I move on to multivariable, a nice way to organize this like way of thought is by writing it out. So you have y is a function of x, right? And then x is a function of t. So like t feeds into x, and then x feeds into y. And if you wanted dy dt, you go from y to t. So I guess how I think of it is when I see dy dt, I think, what are all the ways we can get from y to t in this path? And there's only one way, just literally this line down, right? This might not make sense right now because we only have one path, but you'll see it later when we have more paths to get from one variable to another. Okay, so this is the path we're going to take. Now we take it in increments. So to get from y to t, first you have to go from y to x. So you got to go dy dx, that's this term right here. And then to get from x to t, you got to do dx dt. So that's this term right here. And then you multiply them. All the increments, so dy dx and dx dt in one path, you're going to multiply them. If you change a path, you're going to be adding products. You'll see this in a moment. So let's take an example slightly harder. This is a multivariable example, just so you could see what I'm talking about. So if f is a function of x and y, and it's just x plus y, and then x is 3t plus 1, and y is just natural log of t. You could get, and we wanted to find df dt. Right, I suppose it would be a partial derivative in this scenario since you're working with multiple variables. You could do two different things. You could literally plug in these functions for x and y and take the derivative. So you'd see that 3t plus 1 plus ln of t equals f, which is now a function of t. Now taking the derivative with respect to t is going to give you 3 plus 1 over t, right? So that's df dt. Or you could do the chain rule that we were talking about. So let's draw our tree diagram out. Move this computer. So if you have f, that's where you're starting. And then f is a function of x and y. And then x and y are both functions of t. So now this gives us two different paths to get to t. So we write down partial f, partial t, which is what we want to find, right? Now that's going to be equal. Now what are all the ways we can get to t? So we could start at f, then go down to x, and then go down to t. Or we can start at f again, go to y, and then go to t. So those are two paths. So let's take this first path through x. So to get from f to t, we got to take these increments. So first increment is partial f partial x, right? And then the next increment is going to be from x to t. So that's just, well, I guess it's not a partial this time since there's only one variable in this equation. It's just x of t. So you don't need to write a squiggly d this time. He could just be a normal d. But he's dx dt, right? So from f to x and then from x to t. Okay, now let's take a look at our other path. We're going to stop multiplying now and we're going to put a plus sign. Okay? This indicates that we're switching the paths we're taking. Okay, so now we're going from f to t, but through y. So you're going to have to do partial f partial y times, now from y to t, you got to do dy dt. And those are all of our paths. So now let's take this. So partial f partial x, that's just 1. So that's right, because if we look at this with respect to x, we ignore y, that's just 0. Derivative of x is with respect to x is just 1, so you have 1 times dx dt, which is just 3, plus partial f partial y, which is also 1, times dy dt, which is just 1 over t. So we get 3 plus 1 over t, which matches our other method. So we know it's right. So yeah, that's basically the chain rule. Now you could make this a bit more complex, of course, which is what they like to do on tests. So I have another example here. So if you have z equals sine of x plus y squared, and now x is a function of u squared minus v, and y is a function of e to the u plus 2 ln v, then let's find partial z partial v. So I'm sure there's a way you could find partial z partial v by plugging these in. Well, yeah, actually it's not terrible. It's not terrible, but it can get messy because you're going to be plugging this in. You're going to have to take a nasty chain rule. You're going to have to take some chain rules. So you can definitely do that. Sometimes on the test they'll make it so you can't do this route where you just plug it in and take the derivative. And how they will do that is by, I actually have an example later, you'll see what I mean. But yeah, so if we want to take the traditional route, what they want us to do is we would draw a tree diagram again. So we want to get from z to v. So z is a function of x and y, but x and y are both functions of u and v. Right? This is, I think, the most complex kind of tree diagram you could expect. So yeah, okay, so let's write down what is partial z partial v equal to. So he's going to be, now look, we want to get from z to v. So from here to here. Again, like the previous example, there's only two routes we can take. We can go through here, or we could go through here. Okay? So let's just go through x. So that's going to be partial z partial x times partial x partial v. This is a partial derivative this time since x is a function of two variables. And then you're going to add this to your other route, which is through y this time. So partial z partial y times partial y partial v. Okay. So yeah, we can go through this. So we're going to use shorthand notation, right? Zx. Zx is just going to be cosine of x plus y squared. And then zy is going to be 2y cosine x plus y squared. Now partial, or I guess if you really want to, xv is just going to be -1. And then, and then yv is just going to be e to the u is a constant, which is going to be 2 over v. Okay. So if you plug these in, you're going to have cosine. It's going to be negative cosine x plus y squared plus partial z partial y, which is this guy, times this guy. So it's going to be 4y over v times cosine of x plus y squared. Right, let me double check I didn't make a silly. Zx times this guy, yep, that's negative that, plus zy, so this guy times this guy, that's going to be 4y over v, yep. Okay, so yeah, that's what partial z partial v is. Now, what they would typically expect for you to do now, what they typically expect for you to do now is notice how our function right now is a function of three variables, x, y, and v. And if these functions were written differently, we would maybe even have u in here. We want all of these to be in their simplest form, meaning you want this whole thing to be in terms of u and v. So you'd be plugging these functions in. Now, just for convenience's sake, you could, let's see, x plus y squared is equivalent to u squared minus v plus e to the u plus 2 ln v squared. And then you could factor out cosine of xy squared. So you'd have cosine of u squared minus v plus e to the u plus 2 ln v. Oops. Yeah. Squared times 4y over v, 4 e to the u plus 2 ln v over v minus 1. So that's partial z partial v in its simplest form. Yeah, I really don't think they would get this ugly on a test, but that's how you do it. Just keep in mind you got to plug in the simplest form. So yeah. Okay, so that is all of the chain rule stuff. Yeah, they really can't make it too difficult on you. I always just do the tree diagram no matter what, just to be extra sure that I have the path down right. But yeah. Okay, implicit differentiation is way easier. We can start with something that's like, how do I say this? I think one of the things they teach you is kind of extensive and it's too much work, and you can just literally do the Calc 1 approach. So what they tell you to do, or at least what my teacher had me had taught us in my class, is if you have a function of, okay, maybe it's easier to just give an example. But if you have like x squared plus 2y cubed minus z squared equals 5, and implicitly z is a function of x and y, then you could rearrange this and say this big function of x, y, and z is x squared plus 2y cubed minus z squared minus 5 equals 0, which equals g of x comma y. And you could say this because because z in itself is a function of x and y. So that's what this means. So then after this, say you want to find I don't know, dg dy, right? I guess partial g partial y. Then you could do a chain rule, which is going to be, well, let's see, you have g, well, you have f, which is a function of x, y, and z, x, y, and z is a function of x and y. And I'm put g here because f is equal to g, right? Okay. So now you want dg dy, which is just df dy pretty much. So you could do this, or you could do this. So you have partial f partial y plus partial f partial z partial y. Right? And then you figure out that no matter what values of x and y you plug in to g, you're going to get 0. So this all equals 0. Then this whole thing, this guy is equal to 0 as well. And then what do we want? Remember, we want, we were looking for dz dy. So we want to isolate this guy. So partial z partial y is going to be minus the partial derivative of f with respect to y over the partial derivative of f with respect to z. So yeah, this is the whole approach they have you do, which is way too much in my opinion. What you can do alternatively is quite literally the Calc 1 approach, where say, wait, I had an example written down. Let me see if I could find it. X squared plus 2y cubed minus z squared minus 5. X squared plus 2y cubed minus z squared equals 5. Is that what I said? Let me double check. Yep. Okay. So this is just a simple example. And say you wanted partial z partial x, assuming z is a function of x and y. Right? So you could do the whole big approach. You're going to get this result that we just got. Except it's going to be minus fz over, or minus fx over fz. So partial z, if you just look at the formula. Right, because earlier we were looking for partial z with respect to y. And it was minus fy over fz, but now we're looking for x, so I just switched the letter. So yeah, if you do this approach, you're gonna have, let's see, Now the derivative, oh, and f was defined as moving this guy over. It's just a constant, so it doesn't really matter. But yeah, with respect to x, you're going to have minus 2x, 0, 0, 0. Okay, so that's that. And now with respect to z, you have 0, 0, minus 2z. Okay, so that's the derivative that we're looking for. And yeah, it's pretty quick if you could remember the formula. Another really neat thing you can do, which makes this really, really easy, is just literally treat it like Calc 1, where like in Calc 1, say y is a function of x, and then you had like x squared plus y squared equals 4, and you wanted dy dx, then you would do 2x plus 2y times dy dx equals 4, and then you'd isolate dy dx. In Calc 3, if you want partial z partial x, you would do the same thing. So take the derivative with respect to x. So it's going to be 2x, but it's a partial, so this y term is constant, so it's 0. Derivative of this guy is going to be minus 2z, but remember it's an implicit variable, so you're going to tack on a partial z partial x, and then this equals 0. You could kind of see where this is going. If you isolate partial z partial x, you're going to get equals, well, minus 2z equals minus 2x. And then you could isolate it a bit further and get that partial z partial x equals x over z, which matches this. So yeah, if you remember the formula, this is great and all, but this is not hard at all to do either. It's literally just the Calc 1 approach. So yeah, okay, now we could hop into some practice problems. First one I have 2 chain rules and an implicit one for us. This problem is kind of interesting because, yeah, typically with these chain rule problems, they'll give you, actually, I don't know why this says it falls under gradient vector. Anyhow, oh, I guess because it's a directional derivative, maybe? I don't know. Or, yeah. Okay, that's for later, but you can do this with just a chain rule. So they give you a function for temperature at a certain point. So it's T of xy equals x cubed times y. And then they tell you your position is this vector, this parametric function. And they want you to find they tell you find the rate of change of the temperature with respect to time at t equals 2. Okay, so what is the rate of change of the temperature with respect to time? That's just partial big T, partial little t. So how would you find that? Well, you know that t is a function of x and y, and then your x and y position is a function of, what do you call it? Is a function of t. So both of these, of little t. So both of these are like that. And this is instantly a chain rule problem. You could even do the really easy route and just plug these guys in here. So you'd get t of little t is t cubed times t squared, which is t to the 5th, and then partial big T, partial little t is 5t to the 4th, and they told you at t equals 2. So this is 5 times 2 to the 4th, which is just 5 times 16, and then what is that? 5 times 12 is 60, 70, 80. It's 80. Right? You could do that. you can also, what is it? Yeah, just do this, the tree diagram, and to get from big T to little t, you could do partial t, partial x, dx, dt, plus partial t, partial y, dy, dt. Do all that, you're also going to get the same answer. But yeah, so this is 80, this is option E. Yay. Yeah. Okay. So yeah, I think, I actually haven't tried it with the gradient vector, but I think you could do it like maybe a directional derivative of some sort. I actually want to try this, hold on. The gradient of t. I'm not sure if the units would line up. I haven't done this in a while. We'll see. Okay, with respect to x, it's going to be 3x squared. Y, with respect to y, it's just x cubed. So it's going to be the gradient dot the vector. So at this point, it's going to be at t equals 2. Wait, so your position is 2, 4. So this is going to be 2 over 4 plus 6 root 20, comma 4 over root 20. Is it a unit vector? I'm not sure if it's supposed to be a unit. Anyhow, just for funsies, let's try this. So this is going to be 3 times 4, 12 times 4 is 48, comma 8. Dot these, you're going to get 96 over root 20 plus 60 or 32 over root 20. This is probably not even right. Yeah, no, that's not right. Okay, I didn't expect it because this is a directional derivative. It's not within that direction, it's at a point, so I don't know why I was thinking that. I was just kind of curious because this does say gradient vector, but I don't see how it relates to that. Anyhow, next problem. This is the kind of problem that they, this next problem is what they really like to ask. And I think it's what I had on my test. And I think it's also the hardest they can get. Not because it's hard, but because it's tedious. So they give you this table. I'm going to have to write out the exact format and explain why I really hate this kind of table, because I honestly think it's kind of unfair. If you had never practiced these kinds of problems before, then I think it's a guaranteed thing you're going to get wrong, because there's a lot of things that are implied with this kind of function, or with this kind of setup, problem setup. So they give you this, and they tell you if f is a differentiable function of x and y, so f is a function of x and y, and then they give you another function. They say g is a differentiable function of u and v. So g is a function of u and v, but g of u and v is equal to f of u plus 2v cubed plus 1, comma e to the u v minus 1. And then they want you to use this table up here to find the value of gv at this point. So this is just partial g, partial v evaluated at -1, 0, right? So that's what they want you to do. The best, okay, so what they don't tell you is that these points right here are actually x and y values. They don't write this on the exam. these values right here are in x and y, not u and v. So what a lot of people will fall for is they'll be like, oh, this is u and v. And they'll look along this line because they're like, why do we need 0, 0? 0, 0 is nowhere to be found. We want -1, 0, and they're going to do this. And then you're going to get it wrong, which is really scummy. So keep in mind that these are in x and y. These are not u and v. Okay. So an important thing to note here is that, honestly, the only thing you need to conceptualize is that this g function that's really important to us, it's equal to this function of f. And f was originally in x and y, right? So this is like our x component, and this is our y component of that function. And so and because these are equal, this is kind of like saying we have g, which is just a normal function of u and v, and then we have f, which originally was a function of x and y, but we changed him to be a function of u and v. But now they're equal. So if you find partial f, partial v, that's actually equal to partial g, partial v, because the functions as a whole are equal to one another. And noticing that distinction is what allows you to draw your tree diagram. Okay, so now you have f, which is, it's a function of x and y, and then both of these guys are functions of u and v, right? Or I guess if we write it from the very beginning, partial g, partial v is equal to partial f, partial v, which is equal to partial f, partial x, partial v, plus partial f, partial v, or partial y, my bad, partial y, partial v, right? If we do the whole path we want to get from f to v, so we can go through x, we can go through y. Okay. And this is what the table you need is. So, okay, so let's find fx when x and y are -1, or when u and v are -1 and 0. Because that's what the problem is saying, right? That we want to find this, and this is when u and v are -1 and 0. So yeah, so if we look at this table up here, these points are in x and y, but we don't have xy equals -1, 0. We have uv equals -1, 0. So in order to get x and y values, we have to use these functions that give us right here. Okay, so when u is -1 and v is 0, and you plug them into this x function, you're going to get -1 cubed, which is -1 plus 1. That's 0. Okay, and then y is going to be e to the 0 minus 1, which is also 0. And look at what they give you. It's the other line. It's x and y are 0, 0. This, which for some reason they don't want to tell you that these are x and y values, and it really trips people up. Okay, so now we have that, and we want fx. Fx is 5 here. They tell you. So it's 5. Okay, now we want partial x, partial v. But that's not in the table. We could still find it, though. You just have to take the derivative of this guy with respect to v, which is going to be 3 times u plus 2v squared times 2. Okay, and now we plug in u and v in order to get this. And what are u and v values? They're -1 and 0. So you're going to have -1 squared times 2, which is 6. So this is 6. Now you're adding. Now we want partial f, partial y. They give it to you. It's 7 plus 7. And now we need partial y, partial v. They give you y, take the derivative. So you have e to the uv times, let's see, uv, we're treating u as a constant, so it's going to be times u. Okay, and then if you plug in -1, 0, you're going to get e to the 0 times -1. So this is -1. Okay, plug them in here. You're going to get 30 minus 7. That's 23. That's your answer. So that's option C. Yay. Okay. So yeah, important things for this problem is, yeah, just make sure you realize that these are x and y values. If you really want, ask like a proctor, like, are these x and y? I actually don't think some of the proctors might know, unless maybe it's a professor. Unless the professor's there, he might actually answer this. But keep note of this. Keep note of this. I think that's what makes this problem not hard, but really tedious. I think it's a stupid reason for a problem to be difficult. So yeah. Okay, next problem is going to be implicit differentiation. Okay. They only have 4 on boiler exams, but they're all kind of similar. This one's still pretty good though. I think it's kind of hard. Okay, so they tell you z is a function of x and y, and then they give you this: x plus y plus z plus sine of x, y, z equals 3 plus pi over 2. Okay. And they tell you that z evaluated at 1, 1 equals pi over 2. This is handy later. And then they want you to find partial z, partial x, which they write in the problem as this, at 1, 1. Okay, so we're going to take the Calc 1 route. It's way easier. I think, what is it? You could also do minus fx over fz. Is that what it is? Yeah. Yeah, let's just do this, honestly, because when I was doing it earlier, it was kind of a doozy. But yeah, okay, let's just do this formula. If we really want to, we can do both. But okay, so with respect to x, this is 1, this is 0, this is 0. So you're going to have -1, and then this is going to be plus cosine of x, y, z, and then this is going to be yz right here. Okay, over, with respect to z, so this is going to be 0, 0, 1, plus cosine of x, y, z. Don't forget the chain rule. Chain rule. It's the best rule. So you take, yeah, so you take the derivative of the inside with respect to z, you're going to get xy. Okay, now you plug in 1, 1. So you're going to have -1 plus 1 times pi over 2. Right, because when x and y are 1, 1, z is pi over 2. So that's why you're plugging in pi over 2. Times cosine of pi over 2 over 1 plus 1 times cosine of pi over 2. Right, the cosines of pi over 2 because you have a z in here and the other ones are 1. 1 times pi over 2, that's just pi over 2. And we know that cosine of pi over 2 is 0. So this whole term turns to 0. This whole term turns to 0, and you get -1 as your answer. Which, yeah, it is way faster. Yeah, it is way faster than doing the Calc 1 way. But yeah, that just comes with remembering the formula. It just makes way more sense to me to do the Calc 1 way. And you would take the derivative 1 plus partial z partial x plus cosine of xyz times, you're going to have yz plus, what is it? Yx partial z partial x equals 0. And then you would isolate pretty much. So you'd have partial z partial x plus xy cosine. I'm distributing the cosine thing right now. Partial z partial x, and now I'm going to move out this term and the 1. That's be -1 minus cosine of xyz. And on this part, you could just factor out this -1, in which you'd get that. And then factor out partial z partial x times 1 plus xy times cosine of xyz equals -1 times cosine of xyz. And then divide. And you get the, why did I write it like that? What the hell? -1 plus, okay, that's really ugly. Okay, -1 plus cosine of xy z. Oh, and then this is yz, my bad. Yz right here. Yz cosine xyz over 1 plus xy times cosine of xyz, which is what we had earlier, right? Up here. These are the same thing. But yeah, those are the two ways to do it. Okay, I hope you guys enjoyed this video. I know I haven't uploaded in a while. I had a pretty busy week, and I also did not want to film this video because this isn't my favorite topic. It's kind of lame. But I needed to because, let's see, how many lessons? Oh yeah, next lesson's cool. The 2 next lessons are cool. They're the directional derivative and the gradient, and then tangent planes and linear approximations. And then the next 2 are kind of lame. Actually, the next 3 are kind of lame. They're max and min problems, and then Lagrange multipliers. But then after that, we're getting double integrals, triple integrals, integrals in mass. Yeah, it's gonna be fun. We're getting to like my favorite part of the whole course. So, okay, yeah, no, as always, give me suggestions. Let me know what to improve. But yeah, thank you for watching. Bye.